Here in section 11.8, we're going to be exploring power series. And this topic will be fundamental for the next 4 sections of this chapter. So the remaining sections of this chapter will be focusing on power series and different ways to use power series. So what is a power series? A power series is a function of the form c0 plus c1x plus c2x squared plus c3x cubed, and so on. And what that really is it's an infinite series where the variable x is a power function of the form x to the n, and cn are its coefficients. So it's an infinite sum of power functions. And essentially we can think of it as an infinite polynomial, right? Because polynomials are made up of terms like this, and so this is an infinite polynomial. And what we really have here is this form is a power series centered at 0. Okay, but more generally, here we could, instead of x, we could replace x with x minus a, so this would be a power series that's centered at a. So one question we might have is, for what values of x does this infinite series converge? And that's maybe one we can try and answer here with a simple example like this. Consider the series x to the n from n equals 0 to infinity. So this is just the series 1 plus x squared plus x cubed, and so on. And we recognize this is the geometric series with a common ratio of x, right? Because we're just multiplying x to generate the terms of the series. So it's a geometric series with r equal to x. And so we know this will converge when the absolute value of r is less than 1. So in this case, when the absolute value of x is less than 1. And if it does converge, then we know the sum of the series will be a over 1 minus r. First term here is 1, so it'll be 1 over 1 minus, in this case, r is x. And this will be what it converges to when x is when the absolute value of x is less than 1. So what about a series like this? For what values of x does the power series n factorial x to the n converge? To answer this question, maybe we should use a different approach. Notice that it has n factorial in the series. So when we see n factorial, sometimes it's helpful to consider doing the ratio test. And moreover, it has an x to the n in the series as well. So that is also another indicator that the ratio test would be a good way to try and find solutions or to find values of x for which the series is converging. So when we apply the ratio test here, we'll take the limit as n approaches infinity of an plus 1 over an. For this example, we'll treat n plus 1, or so n factorial x to the n, we'll treat the n as the index here, so it'll be n plus 1 factorial x to the n plus 1 for an, or sorry, for an plus 1. And for an, we'll put n factorial x to the n. And now we can simplify this. Now we know, for instance, here, x to the n divides with x to the n upstairs, so we're just left with x in the numerator. n plus 1 factorial we know is n plus 1 times n factorial. So then we can divide out the n factorial in the denominator. So what remains, we'll have n plus 1. And then here, remember there were absolute values, so we'll keep it in absolute value. So the absolute value of x is what remains in the numerator there. And what we notice is that as n goes to infinity, n plus 1 goes to infinity. And so this would possibly be equal to infinity, except there's one case when it doesn't go to infinity, and that's if x is equal to 0. So it'll be equal to 0 if x is equal to 0, but it'll equal to infinity if x is not equal to 0. Because if x is equal to 0, then 0 times any value will always be 0, so this limit will approach 0 in that case. And so what we notice is that the limit that we get here from applying the ratio test will equal to infinity if x is not 0. So that implies that here the series is divergent when x is not 0. But it is convergent when x is equal to 0. So there's just this one value of x where we know the series will converge. Otherwise, any other value of x, it will diverge. What about this series? We've got the series x minus 3 to the n over n. And because it has this x minus 3 to the n power, again we can apply the ratio test here, and it should give us a good conclusive result. So let's see what we get when we apply the ratio test in this case. Oh, and I have to be careful here. We're taking the limit as n goes to infinity of an plus 1 over an. And here, putting in n plus 1, I have x minus 3 to the n plus 1 over n plus 1. And then divided by an, we'll just flip it over. So it's n over x minus 3 to the n. Now let's simplify here. I can divide out x minus 3 to the n with n of the x minus 3 factors here. So now I have the limit as n approaches infinity. N over n plus 1. And then here x minus 3, which we'll leave in absolute values. Okay, notice that x minus 3 here is constant relative to the limit. The limit is taking n to infinity. So essentially here the x minus 3 can be pulled aside while we consider this limit. If I divide out the n from the numerator and denominator, I can write it as 1 over 1 plus 1 over n. And of course 1 over n goes to 0. So I'm just left with 1 over 1 plus 0, which is 1. So this will be just equal to the absolute value of x minus 3. Okay, so this is the limit that we get after applying the ratio test. And the result that we're looking for is to figure out which values of x will give us a convergent series. And so in this case we know it'll be convergent when this limit comes out to be less than 1. So remember that this result here is guaranteeing that the series will be convergent. Right? And actually in this case it'll be absolutely convergent for the values of x that satisfy this inequality. And let's be a little more specific about what values of x this includes. So this includes any value of x such that x minus 3 is between -1 and +1. So there I'm opening it up so that I can remove the absolute values. And then adding 3 here, here, and here, we get x must be between 2 and 4. So we know it's absolutely convergent for values of x between 2 and 4. But one thing we should also consider is, what about when this limit is equal to 1? Remember, in that case, the ratio test is actually inconclusive. So it's very possible that at the points that make this ratio equal to 1, or that make this limit equal to 1, it's very possible that it converges at one of those points as well. And notice that those values that make this equal to 1 are going to be the endpoints of this interval. So for instance, when x equals 2, right, we get 2 minus 3 is -1, and then the absolute value of 2 minus 3 is +1. And so if it's equal to 1 at x equals 2 there, we need to test separately. So we'll test the endpoints here separately. Instead of of course, we can't use the ratio test to test the endpoints, but we'll now consider what happens when I put x equals 2 into the original series. So if I replace x with 2 in the original series, then I get 2 minus 3 to the n over n, which is really the series -1 to the n over n. And notice that this is a alternating harmonic series, so we know this is convergent. So we know it's convergent by the alternating series test. And then we should also consider testing at the other endpoint. So we want to see what happens when we substitute x equals 4 in. So then our series becomes, let's see, 4 minus 3 to the n over n, which is just 1 to the n. So 1 to the n is just always 1. So it's just the series 1 over n, and we know this is the harmonic series, so we know it's divergent. It's a harmonic series. So we see the complete interval of all the x's for which it will converge will be any value of x that's in between 2 and 4. And we showed here that at 2, at x equals 2, it's convergent, so we should include that value. And at x equals 4, it's divergent, so we should not include that value. But any value of x in between there as well, it'll converge.